Today, scientists are now able to take a small biopsy from a patient and collect neural stem cells. A simple outpatient procedure is all that is needed to start this process. These adult stem cells have the advantage of being immunologically identical to the patient intended for treatment, eliminating the need for a lifetime of immune-suppressing drugs, as well as avoiding the controversy surrounding the use of embryonic stem cells. Once a biopsy has been collected, billions of stem cells can be propagated from this single tissue sample. These new stem cells can then be manipulated to become specific neural cells and support cells needed to repair the brain and spinal cord. As seen here, damage to the spinal cord prevents messages from being sent by the brain or received from the lower body. Stem cells can now be administered to treat the injured portion of the spinal cord. Once the new cells have integrated into the host spinal cord, these new cells will be able to replace lost neurons or help non-functioning neuronal cells to function once again. After the stem cells have bridged the injured area and healing of the spinal cord has transpired, signals can be transmitted to the lower portion of the body. This treatment will restore function, allowing a patient to walk and feel again.
Experts say the study is significant for two reasons. First, it used adult stem cells and not embryonic stem cells. And second, the bioengineered follicles were fully integrated into the surrounding tissue, something that has not been managed before. These bald research mice are offering new hope for humans who suffer from hair loss. Researchers in Tokyo, led by Takashi Tsuji, say they've succeeded in growing hair on the mice by transplanting bioengineered tissue under their skin. The scientists created what's called hair follicle germs, primitive tissue made from two types of cells in adult mice. The cells were then implanted just under the skin of the naturally bald mice. 3 weeks later, about 3/4 of the follicles grew black hair. Toronto hair specialist Dr. Cam Simmons says in the past, researchers have focused on transplanting the cells at the base of the hair follicle and relied on existing stem cells from the skin to interact.
In the study that was reported in Nature, they're using stem cells from both areas, so it is a newer approach.
The newly grown hair also sustained hair cycles comparable to those of the mice that the cells were taken from, so when dead hairs fell out, new ones took their place. They even developed natural functions such as standing on end, showing they had integrated with the muscles surrounding the hair follicles. Dr. Tsuji says right now this process is only done in his lab, but his team is hoping to adapt the process to humans within a decade.
طريقة جديدة لعلاج الأورام الخبيثة من خلال إشعاع البروتونات تثير جدلاً في عدد من الدول، إلا أنها مطبقة في الكثير من الدول المتقدمة. فقد أعلن الخبراء أن علاجاً إشعاعياً جديداً لمرض السرطان بالبروتونات قد يثبت فعالية كبيرة، لكنه لا يصلح إلا مع أورام نادرة. وتتلخص طريقة العلاج بالبروتونات بحقن إيوانات من عنصر الهيدروجين في جهاز تسريع الجزيئات والمسمى سيكلوترون، وتسليط الجزيئات الناتجة على الورم الخبيث مباشرة. تختلف هذه الطريقة عن العلاج الإشعاعي بأنها أكثر دقة وتصيب الخلايا السرطانية فقط، لكن الخبراء يحذرون من أن العلاج وهو طريقة أكثر تحديداً مقارنة بالإشعاع العادي لتدمير الخلايا السرطانية باستخدام الإشعاع البروتوني ينطوي على مزايا إضافية، ولكن لقلة قليلة من حالات الإصابة بالسرطان. ولم يعلق الخبراء على الفور على حالة الطفل البريطاني، لكنهم قالوا إن نوع سرطان الدماغ الذي أصيب به لا يتماشى عادة مع العلاج الإشعاعي بالبروتونات. ويقول الخبراء إن العلاج الإشعاعي بالبروتونات ليس أكثر فعالية على الخلايا السرطانية من العلاج التقليدي بالإشعاع، لذا فهو ليس عصا سحرية. يستخدم هذا النوع من العلاج أشعة البروتونات وليس أشعة إكس أو الفوتون، ويوجهها صوب الخلايا السرطانية لقتلها، وتوجه البروتونات إلى الورم بطريقة أكثر تحديداً مقارنة بأشعة إكس. وبخلاف العلاج التقليدي بالإشعاع، تتوقف أشعة البروتونات بمجرد أن تصيب الهدف ولا تظل بداخل الجسم، مما يجعلها أقل ضرراً على الأنسجة السليمة.
Today, cancer is treated with a wide variety of methods, but these methods are often as toxic for the body as they are for the tumor. Now, however, there is a way to enhance tumor cell death without adding toxicity in standard radiotherapy. Nano X-ray nanoparticles are incredibly small crystals, so tiny that 5,000 could fit around the perimeter of a human hair. These crystals are surrounded with a soft protective layer, minimizing unwanted interaction with the body, and suspended in a water-based solution. In nano X-ray treatment, the particle suspension is injected with a standard syringe directly into a tumor, where the nanocrystals accumulate and wait for activation. At this point, the patient that received nano X-ray has a major advantage over a standard radiotherapy patient. That's because during standard radiotherapy treatment, the body is exposed to X-rays. X-rays react with water to produce free radicals, which in turn destroy DNA and other molecular structures, killing cells. Unfortunately, these free radicals destroy healthy cells just as well as cancer cells, and radiotherapy is therefore limited by the healthy tissue's damage. But in nano X-ray therapy, standard X-rays activate the nano X-ray particles in the patient's tumor. The nanocrystals are optimized to absorb more X-rays and produce many more free radicals than water, damaging the tumor cell's DNA and cellular structure more severely than the surrounding healthy tissue. Because of the nanoparticles, the X-ray's effect is amplified and localized within the tumor, allowing for a targeted strike against cancerous cells. While healthy tissues receive the standard dose of radiation, the tumor dies much more quickly. Just one injection of nanoparticles can amplify several radiotherapy sessions, shrinking the tumor over time. Because it uses standard radiotherapy equipment and works with a purely physical principle, nano X-ray therapy can be used to fight a wide variety of cancers. Nano X-ray is the next step in radiotherapy treatments, and it's brought to you by Nanobiotics.